An electron goes through a wall, not around it, through it. It can be in two places at once. It has no definite position until you look at it, and the very act of looking at it changes what it does. Two electrons, separated by the entire width of the universe, can be linked so tightly that measuring one instantly affects the other. And not one physicist alive can fully explain why any of this works. Quantum mechanics is the most accurate scientific theory ever produced. It has been tested to a precision of 1 part in a billion. Everything from lasers to MRI machines to the processor running your phone depends on it. And its core claims, if you actually stop and think about them, are completely insane. This is all of quantum physics, in 15 minutes. The first rule quantum mechanics breaks is the one that feels most obvious. The idea that things exist in one place, doing one thing at one time. In everyday life, a ball is either here or there. A coin is either heads or tails. A light switch is on or off. We call this classical physics, and it describes the world you can see and touch with extraordinary accuracy. Newton figured most of it out in the 1680s. For objects above a certain size, it still works fine. But around the late 1800s, experiments started returning results that classical physics could not explain. Light didn't behave like a wave in some situations. Heated metal didn't glow the way the equations predicted. Electrons knocked out of metal by light followed rules that made no sense under classical theory. Something was wrong at small scales. What followed was 20 years of confusion, genius, and several Nobel Prizes. The result was quantum mechanics. Here is the first thing it says, and the first thing that should break your brain. Fire a single electron at a barrier with 2 slits in it. The electron is one particle. It should go through one slit or the other. Instead, it goes through both simultaneously, interferes with itself like a wave, and lands on the screen behind in a pattern that only makes sense if the electron traveled through both slits at once. This is the double-slit experiment and has been confirmed thousands of times. It works with electrons, atoms, molecules, and photons. The interference pattern is not a statistical illusion. It is a real physical signature of a single particle spreading through space as a wave, interfering with its own possible paths, and only resolving into a single location when it hits the screen. Now here's where it gets worse. Put a detector at one of the slits to find out which one the electron actually went through. The interference pattern disappears. The electron stops behaving like a wave and starts behaving like a particle, going through one slit and producing a normal, boring, two-stripe pattern. The act of measuring which path the electron took eliminated the wave behavior. The electron behaves differently depending on whether you are watching. This is wave-particle duality. Everything at the quantum scale is neither purely a wave nor purely a particle. It is both depending on how you interact with it. The question, is it a wave or a particle, is not a question with a fixed answer. It depends on what you do to it. This leads directly to the second major idea, superposition. Before you measure a quantum particle, it does not have a definite state. Its position, momentum, and spin are not hidden from you because your instruments are imprecise. They genuinely do not exist as single values. The particle is in a superposition of all its possible states at once, each with a certain probability. Only when you make a measurement does the system resolve into one outcome. Erwin Schrödinger, who helped build quantum theory, found this so absurd that he invented a thought experiment to mock it. Imagine a cat sealed in a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the vial and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics says the atom is in a superposition of decayed and not yet decayed until measured. So, by extension, the cat is in a superposition of alive and dead until you open the box. Schrödinger intended this as a reductio ad absurdum. He was trying to show that superposition could not possibly apply to macroscopic objects. Physicists largely agreed, but then disagreed violently about why and where the boundary is. That argument is still going. The cat thought experiment, meant to disprove quantum weirdness, ended up as the mascot for it. The third cornerstone of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg in 1927. It states that you cannot know both the position and the momentum of a particle with arbitrary precision at the same time. The more precisely you measure one, the less precisely you can know the other. This is not an engineering problem. No better instrument will fix it. It is a fundamental feature of how reality is structured at small scales. To measure an electron's position precisely, you need to hit it with a photon of short wavelength, which carries high energy, which kicks the electron hard and scrambles its momentum. Use a gentler photon, and you get less positional precision. There is a hard mathematical floor on how much you can know simultaneously, and it is built into the equations of nature itself. Now, the fourth concept, and the strangest, quantum entanglement. Take two particles and interact them in the right way. Now separate them. They are entangled. No matter how far apart they go, across the room or across the galaxy, measuring one instantly determines the state of the other. If you measure particle A's spin and find it pointing up, particle B will be found pointing down instantly, regardless of the distance. Einstein hated this. In 1935, he co-authored a paper with Podolsky and Rosen arguing that this could not be real, that there must be hidden variables predetermining the outcomes, like a pair of gloves split into two boxes. You open one box, see a left glove, and instantly know the other box has the right glove. No mystery, no spookiness, just information you didn't have yet. In 1964, physicist John Bell proved that the glove analogy is wrong. He derived a mathematical inequality that local hidden variable theories must satisfy. Quantum mechanics predicts that inequality will be violated. Experiments by Alain Aspect in the 1980s and dozens of experiments since all confirm the same thing: Bell's inequality is violated. The correlations between entangled particles are stronger than any pre-programmed plan could produce. Entanglement is real. The particles are genuinely connected across space in a way that has no classical equivalent. This does not allow faster-than-light communication, because the outcomes are random. You cannot control what results you get when you measure, so you cannot use entanglement to send a message. But the underlying connection is real, and it is not explained by anything in classical physics. That brings us to the fifth and deepest problem: the measurement problem. All of quantum mechanics runs on a mathematical object called the wave function. The wave function evolves smoothly, deterministically, according to the Schrödinger equation. It spreads out over all possible states, tracking probabilities. Then a measurement happens, and the wave function collapses. One outcome: everything else disappears. But the Schrödinger equation does not contain any collapse. There is no point in the math where the wave function suddenly snaps to one value. The collapse is added by hand as a rule without a physical explanation. This is the measurement problem. We have an equation that describes quantum systems perfectly, and a rule that says when you look at them something different happens, and no physical theory of what that different thing actually is. The most widely taught answer is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. Copenhagen says, stop asking what the wave function physically is. It is a tool for predicting measurement outcomes. The quantum world and the classical measuring world are separate. When you measure, you get a result. Do not ask what happened in between. Copenhagen works. It produces correct predictions. It is what most physicists use in practice. But it is philosophically empty. It says the universe behaves one way when you look at it and a different way when you do not. And that is simply true, and there is nothing more to say. Other interpretations disagree. The many worlds interpretation says the wave function never collapses. Every time a measurement happens, the universe splits into branches, one for each possible outcome. All branches are real. You, in this branch, see one result. A copy of you, in another branch, sees a different result. All outcomes happen. This solves the math cleanly, but costs an infinite number of unobservable universes. Pilot wave theory says particles always have definite positions guided by a real wave. The uncertainty principle is about our ignorance, not about reality itself. This restores determinism, but requires the wave to act non-locally in a way that still feels strange. No interpretation has been experimentally ruled out. No interpretation is universally accepted. The most successful physical theory in history describes what happens, but after a century of work, there is still no agreement on what it means. Now, finally, the reason quantum mechanics makes physicists quietly nervous at dinner parties. General relativity describes the very large planets, stars, black holes, the curvature of space-time itself. Quantum mechanics describes the very small particles, photons, forces at subatomic scales. Both theories are spectacularly accurate in their own domains. They have never been caught being wrong. They are also fundamentally incompatible. General relativity treats space-time as a smooth, continuous fabric. Quantum mechanics says that at small enough scales, nothing is smooth or continuous. Everything is grainy, probabilistic, and uncertain. Try to apply quantum mechanics to gravity the same way it is applied to electromagnetism, and the equations produce infinities, not big numbers, literal mathematical infinities, which means the theory breaks. String theory, loop quantum gravity, and several other approaches have been proposed to bridge this gap. None has been confirmed by experiment. The two best theories we have, the two theories that together describe essentially everything we can observe, cannot be true simultaneously in the way they are currently formulated. Physicists have known this since the 1930s. They are still working on it. Quantum mechanics is complete, tested, useful, and deeply mysterious. It tells us that at the smallest scales, reality does not have definite properties until something interacts with it, that particles, separated by the width of the universe, can be correlated in ways no classical system can replicate, and that the most fundamental equation we have for describing all of this doesn't explain what's actually happening when you look. You now know all of quantum physics, roughly. In about 15 minutes, the physicists who spent their lives on it would like you to know it bothered them too.